Good morning, everybody. Very nice to see you all, and thanks for the invitation to have me here. This is actually the third time I'm in Mikulov. I'm very pleased to be here again and meeting many old colleagues already from the EPCC and other European collaboration times. But also it's also an opportunity to know also what you are doing here and learning about your work. So what I'm going to talk about today is give you some examples how bird populations are affected by climate change. My examples mainly come from the North European side, but we'll also take these as a kind of examples. Probably the same processes are occurring all around the globe in different parts of the world, also here in the Czechia. So, yeah, the big question is how the bird populations or populations in general are responding to climate change. They have several options. They can move either in time or in space. In time it would mean that they are changing their phenology, the annual cycle of timing and causing like a timing differences. They can also change their positions in space, and these range shifts are pretty well known nowadays in many species. They can also try to adapt to these changes through evolutionary processes. That might be, for example, physiological changes, morphological changes. I'll tell a couple examples in the end, but of course these changes can be quite slow and not necessarily the only option how species can cope with climate change. Then the last way to respond is, of course, the thing that we don't want to happen, is that the species are going extinct, either locally or even globally. And there are already some examples in, for example, tropical amphibians where the global extinctions have been occurring because of the climate change. But on the local scale, local extinctions are occurring all the time, and I tell some examples also on that. But to find out what kind of changes there are occurring, we need long-term monitoring data. I'll give you some examples of the Finnish common bird monitoring schemes where I'm coming from, but also luckily there are similar kind of schemes conducted in different parts of the world. I give mainly examples from the European side, but we need this kind of information to find out how the things are going and then potentially try to mitigate the negative impacts of climate change. In this talk I will concentrate mainly about the winter bird surveys, breeding bird surveys, which are in Finland conducted using line transects. I'll tell a little bit about the nest card scheme, which tells about the breeding events of the species. Also a little bit about the ringing schemes and migration counts. And of course this is how the annual cycle is going, so especially in the migratory species. We have the breeding season, we have the autumn migration, wintering and spring migration. And of course climate change can influence all these kinds of life history events in different ways. And I give you a couple examples on migratory birds using migration data. So first example comes from the black-headed gull. This is data from Hanko Bird Observatory situated in southwest Finland. And you can see on these green and blue lines there's a situation how the migration has been occurring in the 1970s and 1980s and 1990s. So there's the spring migration and here is the autumn migration. And then this is the green lines tells about the more recent situation in the 2010s. And you can see that this peak is occurring earlier. So this is starting of April, so about 10 days earlier spring migration nowadays in this species. But also the autumn migration peak has been advancing. You can see that there's population decline overall, but the autumn migration occurs also early in this species. So they only spend the same amount of time in the breeding areas, and once the breeding is done, they will leave the country. And you can see this an advancing timing of the spring migration and autumn migration time dates. This is the median migration timing. In Whooper-Swan, Cygnus, it's a different story. So here we have a clearly advancing spring migration days as well, But then in the autumn time, these are actually leaving Finland much later, like 10 days later than in the past. So there's a definitely different variation between species, how they are responding. Yeah, that's why we need more information how these are potentially linked with the population dynamics or the range shifts and so on. And we can also look at this on a broader scale. A couple of years ago we aggregated data from Europe and North America, from different bird observatories, and look at how the spring migration phenology has changed in time in these regions. And these data has been collected by doing visual migration counts or standardized ringing, so same year, same protocols are repeated by voluntary bird watchers. And we used this data to measure what's how the start of the migration in the springtime. So this is the early phase when 5% of the migrants have passed place, how the medium migration or the end of the migration when 95% of the migration have passed the migration location. And this figure here shows how the changes have been occurring. So if the birds would be migrating at the same time than in the past, they would these dots and would be placed along this line, this dashed line. But because they are under here the line, it means that they have advanced the timing of spring migration. And this is telling how many days per year the changes have been occurring. So on average about 0.1 or 0.15, so 1 day or 1.5 days per decade is the average speed. And it's mainly advances have been occurring in the early phase of the migration and in the medium migration, but the last migrants haven't advanced their timing of spring migration that much. And this is probably because these are the birds which are really actively moving to the breeding areas to try to breed. And usually the last migrants are unexperienced young birds or non-breeders which don't have that as big a rush to the breeding areas as the early migrants. We also didn't notice hardly any differences between the short-distance migrants and long-distance migrants. So species which are wintering in Europe or species which are going to tropical areas for the winter. There was slight difference in the early phase of the migration period, but not that much. And also the changes were faster in Europe than in Canada, where we had also data. And also the temperature increases have been faster in Europe than in Canada. So it suggests that these are strongly linked with the temperature values changes. But overall, we calculated how fast the average bird, based on this data, has advanced the timing of spring migration through time. And luckily, we have data already since 50s onwards, and it's about 1 week advancement of the median, in the median migration date. And it also highlights that if you would take like a 10 years period, almost in all the cases, you don't see that much differences. But when you have a really long time series, you can really start to see the patterns and gradual advancement in the timing. So similar kind of patterns can be also, of course, looked at from the breeding data. And that here we have used Finnish nest card scheme. Similar kind of data are also collected in many other countries. So in nest card, people are reporting how many eggs or chicks they see in the nest in a given date of different species. And altogether, for example, in Finland since 1960s have been about 250,000 nest cards filled from breeding birds. And based on this, we can look at how the breeding dates have been advancing. And you can see that this occurs both in the residents, in short-distance migrants, and also in the long-distance migrants. But the slopes are steeper in the residents compared to, for example, long-distance migrants. But in any case, all the species as a whole are advancing in timing of spring migration. So they are responding to these warming springs and milder winters. So that was about the change in time. Then what about the changes in space? So in general, there's quite a lot of evidence nowadays that species are shifting their ranges and abundances towards poles and mountaintops. This also occurs in abundances, and not only range boundaries, but also abundances within the range are moving. This also occurs in the non-breeding season, so it also concerns the wintering conditions. But also it's important to understand how the protected areas are actually fitting into this pattern, because as we know, protected areas are static. They don't move every year in a certain direction. But species compositions can change within those ranges, within those areas. I'll introduce the two monitoring schemes that we have in Finland, and similar kind of data has been collected in many other countries. So we have the winter bird survey, which is conducted 3 times in winter. So we have the early winter survey in November, the midwinter around the New Year, and then the late winter, which is in February, March. And in Finland, this is done by walking typically around 10-kilometer long route, where all the birds are surveyed. There's 8 different habitat categories, so we also have information about habitat type, where the birds are observed. Nowadays we also collect sex ratios, like in bullfinches or some water birds, and also mammals are surveyed nowadays. There's about 550 routes surveyed every year, and about 1,000 volunteers are participating in this on an annual basis. And these surveys are part of the International Water Bird Survey, which also is conducted in Czech Republic. So all the water bird information from these surveys are submitted to Wetlands International as a part of the global monitoring. In the breeding season, we have correspondingly the line transect survey. It's only done once in June, and the aim is to monitor the breeding population changes in national level. And we have 50-meter main belt and supplementary belt, which is then possibilities to do some distance sampling. We also have habitat information collected here, and also type of the observations are recorded. So is the bird singing, calling, seen, or for example a bigger flock. And we have nowadays a network of these sites. So based on the coordinates, there's more than 560 locations across the whole Finland, where there's a 6-kilometer line transect, and observers are walking through that. And here is an example. So it's typically 2 times 1 kilometer rectangle, and in quite many cases there's also sections which are inside protected area and then sections which are outside protected area. So we can get also information about what's happening in the protected areas and in non-protected areas. And we have about 200 to 300 of these are repeated on an annual basis, and about 100 volunteers are participating. And this information is sent to the European Bird Census Council, coordinated by the Czech Ornitological Society in Prague. So I get emails every year from Eva to reminding me that now this is the time that I should send my the Finnish data to also on a European database. And of course we should understand that climate change is not the only factor influencing bird population, but also land use has quite important has big importance on population dynamics. And for example, these kind of indicators which are describing this general state of the bird population trends have been developed under the EBCC for a long time. And here are examples from Finland from the wintering season. We can see that there's a long-term increase in the urban birds, especially from 50s till 80s. But since then it has been rather stable or fluctuating. But in the forest there's a long-term decline which is linked to the poor habitat quality of the forest because of the more intensive logging. So these are things that we need to keep in mind as well when we are trying to understand also the impacts of the climate change. So I'll give you a couple examples of the density shift of the breeding land bird species. So these are, here's an example of blackbird Turus merula, where in the 70s and 80s this population was mainly concentrating in the south and west corner of Finland, and there was hardly any birds breeding in the central part of the country, whereas nowadays the population is moving towards north quite rapidly, and this star here indicates the central gravity of the population. You can see that it also has been moving towards northeast. Then another example, northern species, Fringilla montifringilla, which used to be a common breeding bird here in central Finland, and also some sporadic breeders in south, but there has been substantial population declines here, but also in the core breeding areas in the northern part of the country. And again, the blue star showing the central gravity is moving northwards. So when we do this kind of analysis for a large group of people, we can start to see patterns. And we can see that, for example, the residents and partial migrants are moving faster northwards than the true migrants, short distance and long distance migrants. So different species have different speed, and not all the species are doing equally. Also, the body size of the species is influencing. So we can see that there's smaller size species are moving faster than the larger body size species. And this could indicate that because small size species have a shorter generation length, so they're able to respond to the occurring changes faster than the species which have a longer generation time. And overall, we have calculated that how fast these changes are. So on average, in Finland, the birds have been shifting about 15 kilometers per decade towards north. And at the same time, we can also compare how fast the temperatures are changing. And this graph shows that they are not, of course, directly going northwards, but there's also movements towards first northeast and then towards the northwest corner, which have the highest and coldest mountains in Finland. And temperature changes have been actually much more faster than the species movements. So on average, temperature have been moving about more than 70 kilometers per decade towards north. So clearly birds are lagging behind this change. And we have done similar kind of analyses in the mountain regions in the Scandinavia, and how fast birds are moving uphill. And it's about 1 meter per year, the speed in Norway and Sweden, how fast the birds are moving towards the mountaintops. And of course, the same pattern occurs all around Europe as well, in quite a few species. So just to give you an example from the European Breeding Bird Atlas, where we have been able to compare how fast the changes are between the two atlases. And on average there, in Europe, also the center of gravity of the distribution areas have been moving about 1 kilometer northwards between these two atlases from 1980s till more recent times. And here is just an example of one of the extreme species, Savi's warbler, where you can see a lot of these colonizations, blue colors, on the northern side of the species range, and local extinctions on the southern side of the range. And in general, the central gravity in this species have been moving more than 180 kilometers northwards in 3 decades, which is quite substantial change. So here are examples from the breeding season, but there's also a lot of happening in the non-breeding season, and especially in the waterbird section. So this is an example from Taftatak out here, Fulicula, how the population sizes have been changing in Europe in recent decades. And you can see strong increases in the Baltic areas in Finland and Sweden, and severe declines in the western side of the range. For example, in Ireland, France, and Switzerland. And here are same figures from the how large an amount of individuals we're talking about in this species. So we are talking about redistribution of tens of thousands of individuals on European level. We have also looked at this on a multi-species level using the fantastic network on a European scale, including also Czech data. So the idea is to look at how the central gravity of the abundances are moving also between years, but also in the long term. So if there's a positive change, it would be towards, or if the species are moving northeast, it would be kind of a link positive level. And if they're, on the other hand, you get negative values if the distribution area is moving southwards. And here you can see also that not all the species are responding similarly. So long-term changes have been significant in diving ducks, where the speed is about 5 kilometers northeast per year. So even faster than in the land birds that I showed earlier in Finland. But there's hardly any change in the shallow water dabbling ducks or inland farmland species like geese and swans. So especially these 4 species have been responding really fastly. Golden eye, smew, and goosender and tufted duck. We can also look at these changes on a community level. So how the overall community composition is changing through the climate change. And here we have used a method developed by French researchers, community temperature index. And here the idea is to be every single species like jay here or the Siberian jay they have different temperature values, so-called species temperature indices. So in Eurasian jay, the overall temperature inside the breeding range is 14.4, but the Siberian jay, which has a more northerly distribution, the breeding range temperature is 8.2 only. So if you would have a very simple community where there would be only Siberian jays, the community temperature index would be 8.2. If you would have a mixed population of the community between these 2 species, then the community temperature index would be average of these 2 values. And if we would have a community which would be dominated by European jays, it would have the same community temperature value as the Eurasian jay. Of course, in the real world, the communities are formed by tens of different species, so it's a bit more complicated to calculate, but this is anyway the process how it's done. And we can done the similar kind of calculations of the species temperature indices also during the non-breeding season, so naturally, in this case, also the Siberian jay has a colder species temperature index in the wintering season. And we have done also the same thing for the North American species. So we have the values to calculate also the community changes on the North American level. So here is an example from Finland, how in southern Finland the community temperature index has changed since 1950s when the surveys have started. So you can see that it's a gradual increase. Of course, there's a lot of annual variation, but on average, we have started from about temperature value 5, and now we are on the -5, and now we are on the temperature value -3. So these can be linked with also the temperature changes. And similar kind of patterns can be found in many other European countries. So many of the values are showing these kind of increasing trends, which indicate that there's domination of warm-dwelling species compared to cold-dwelling species. And this has been the study period in this when we have been looking at comparing different regions, and we have similar kind of information also from the North American side. And here are the results in a nutshell. So in larger the bubble is, larger is the change, and red colors means positive changes in the community temperature index, and blue colors means negative changes. And you can see clearly already comparing the winter and the summer, that there are larger red dots in the map showing that the winter communities are changing strongly. But in the summertime, the situation is a bit more variable. There are also even negative trends there, but overall slight positive changes in the communities. So clearly, the winter communities are changing much faster than the breeding communities. What could be the reason for this? Perhaps in the wintertime, birds are less site-pedelic, so they are able to move and respond to the climate change much more faster. And if they are more flexible to move, they don't need to be placed in one single site for a long period of time for breeding, like in the summertime. Let's see. For some reason, it isn't moving forward. Okay. So yeah, in the breeding season, birds are tied more to a certain location for a longer period of time, and that's why the changes can be slower, and it might be occurring through the demographic processes. In protected areas, then the last example on the range is about the protected areas compared to non-protected areas. And here we have data collected from Finland in different parts of the country, from the breeding areas, and these are divided into 2 different periods, both inside and outside protected areas, and we use the similar kind of a community temperature index approach. It seems to be working now. Okay, and as you can see here, so here is the in unprotected areas, so this is the period 1, so 1980s and 70s, and this is the more recent time, and you can see that there's an increase in the community temperature index. So the communities are changing outside protected areas. But similar kind of pattern is occurring also in protected areas. But if you look at overall, the communities are cooler in the community composition, so they are holding more cold-dwelling species than outside protected areas. So even though the changes are occurring inside protected areas, the protected areas are still potentially more beneficial for these cold-dwelling species. And to give you a bit more evidence on that, we have been looking at what's happening in these northern species like Fringilla montifringilla on the southern edge of their range, and how the population sizes are changing inside and outside protected areas. And you can clearly see that this is inside protected areas and these are outside protected areas in different time periods. You can see that there's substantial differences in the breeding densities. So there's, for example, on average, larger population sizes of these northern species inside protected areas than outside protected areas. But also the declines have been faster outside protected areas. So even though the protected areas cannot fully mitigate the negative impacts of climate change, they can reduce the speed and give more time for these northern species to cope these harmful changes in the climatical conditions. So the last examples that I have is related to morphology of species. So this is the way how species might be adapting through morphological processes and natural selection to climate changes in the climate. And there are different kinds of hypotheses related to morphology and climatical conditions. And the first one is the Berryman's rule, which suggests that the body size of species are decreasing with temperature. So this is a spatial gradient. So for example, house sparrows, Passer domesticus, are much larger in northern part of Finland than in southern part of Finland. There's about 0.5 centimeter difference in the wing length between individuals in these two different regions. And how this kind of a morphological clean is changing in time is interesting. Then the other one is the Allen's rule, which tells about the appendices of species like bill or legs and how they are linked with the temperature. So typically species and individuals which are occurring in the warmer conditions have longer these appendices. You can, for example, see this like in the herring gull complex, that the northern herring gulls have shorter legs and shorter bill, and then, for example, the Caspian gull has a longer bill and longer legs. Or in chiffchaffs, where the nominate subspecies has a longer bill compared to the Abietinus subspecies. But also within species there are differences. And the third rule is about the Krogel's rule, which is linked to coloration with temperature and rainfall. And here the model example is from the Tornioles, where you have a gray and brown morphs. I'll tell a bit more about that as well. So there's quite a lot of these morphological changes haven't been studied as much as the for example, the phenological changes or the changes in the species distribution areas. But there are some evidence, for example, using museum specimens or ringing data. And in this case study, we have been looking at the wing length of wintering birds in Finland. And overall, there's a decrease in the wing length since 1970s in Finland and Sweden based on the ringing data. So ringers have been ringing birds and measuring the wing lengths for quite some time. And even though the changes are quite small, so we are talking about very small changes in the wing length, we can measure it once we have enough data. And if we look at on species level, 4 species out of 22 show significant decreases, but there are also species which actually have shown increases in the wing length. One of them is the greenfinch, which we know that also on the European level there has been drastic population declines because of the trichomonas parasite. So potentially the wing length change is not related to climatical conditions at all, but more like how this parasite is causing mortality. So potentially the mortality has been even stronger in the small-sized individuals. The other example of the increasing wing length has been a red pole called Carperis flammea. Then the third example from these was morphological differences was the Tornio case. So there's a grey morph and a brown morph, and we have been collecting information from different parts of Europe from the museums. I visited a couple of years ago also in Prague and photographed all the Tornio specimens that occurred in the Natural History Museum, and we then defined what kind of were they grey morphs or brown morphs, and when the specimens was collected. And we could clearly see that there's more grey morphs in the boreal zone, in the northern boreal zone. So these colors are indicating the geographical, the climatical conditions. So blue colors mean the boreal climatical conditions. Green one is the temperate climate, and then the yellow-orange is the Mediterranean climatical conditions. But yeah, grey morphs are more common in the north boreal zone, whereas compared to temperate and Mediterranean zone. And in the northern boreal zone, you can see that there's also increases in the proportion of brown morphs. So there has been changes for quite a few times. These are examples from Finland, but you can also see it on the European level dataset. And there are several reasons why this might be occurring because of the climate change. The grey morphs have a higher survival in snowy conditions, and because the snow conditions is decreasing, they don't get the same kind of benefit anymore from the survival point of view compared to brown ones. The grey moths have also better camouflage in snowy conditions. They could be, for example, vulnerable for predation of the goshawk or disturbance by the small passerines, and that's why the energy consumption during winter time is increasing and causing some additional mortality. If you look at even single feather structure, the grey owls have different kinds of feathers. So they have thicker feathers which are better for insulation, and that's why that could explain, for example, the higher survival in cold conditions. But on the other hand, then brown moths are more generalist and more tolerant for parasites, and that's why they might be better coping in the warmer conditions. So as a take-home message of my talk, I can tell that there's a lot of changes in the phenology. So species are advancing their spring migration and breeding dates, but there are more variable responses in the autumn time. Species ranges and abundances are shifting towards coves and mountaintops. Protected areas can mitigate the abundances to some extent, but not fully stop the negative impacts of climate change. There's also a lot of different changes occurring in the morphology. We don't know as much about these than compared to phenology or the abundant changes, but surely they are occurring. I'd really like to acknowledge all the volunteers who have been doing the data collection and giving a kind of also support for them, that this kind of work that we need to keep on doing and collecting the data sets also in the future. And I thank you for listening, and also some of the funders who have been helping to do this research. Thanks a lot.